Good morning. My name is Dr. Ripon Padgiri. My co-author name is Dr. Molaya Dottabora. We are from National Institute of Technology, Silchar, India. We are going to present HEX-BLOOM, an efficient method for authenticity and integrity verification in privacy-preserving computing. Merkle 3 is applied in diverse applications to verify its authenticity and integrity. Recent developments suggest that Merkle 3 is adopted in numerous research domains, for instance, blockchain. However, Merkle 3 is computationally costly data structure. It uses cryptographic string hash function to partially verify the data blocks integrity and authenticity. Merkle 3 allows verification of data blocks, authenticity and integrity after successfully downloading a particular data block using Merkle root, for instance, peer-to-peer torrent network. Moreover, the time complexity of Merkle 3 is high. In addition, Merkle 3 requires high memory to store hash values. Each block requires a few hash values which require network access. This process creates enormous network traffic. Therefore, it degrades the performance of the Merkle tree and increases the network traffic. We propose an alternative model of Merkle tree to address the above issue. Our proposed model uses HEX exclusive OR and Bloom filter. We term it as HEX-BLOOM for short. We present it in two-fold: first linked as X and second Bloom filter. Merkle tree is array M where Merkle tree order of M. It is rooted and each node can have at most M minus 1 keys. Each node can have at most M children and keys are not in order. Let L be the number of blocks. These blocks are hashed using SHA hash function or any secure hash function. Therefore, an M array Merkle tree has I internal nodes. It shows that there is an overhead of I hash function. The total number of nodes for L leaf nodes is n. M array Merkle tree has height h for n nodes. M array Merkle tree takes big O, log n time complexity to insert a new node or delete a node. The building time complexity of M array Merkle tree is big O of n. The verification time complexity of particular block in M array Merkle tree is big O of log n. The verification time complexity of total number of L blocks is big O of L log mn. The extra space complexity of M array Merkle tree is big O of n. So the key issues of Merkle tree is, let us assume that the set of blocks L consists of millions of blocks. Then it is not feasible for a conventional computer to construct a Merkle tree. Merkle tree construction requires big O of n log n hash function calls, which is time consuming. As a result, it is not feasible for a large set of blocks. Merkle tree cannot be constructed by B3, B plus 3, ABL tree or any other search tree. Otherwise, it will violate the definition of Merkle tree. The Merkle tree requires extra space of big O of n and it is costly due to large size memory requirement per node. Merkle tree creates massive network traffic. Each block requires network access in Merkle tree verification and authenticity. Bloom filter is a approximate membership filter and it can answer yes or no, and that yes or no can be either false positive, true positive or true negative. The time complexity of insertion, query and deletion in Bloom filter is big O of k, which is approximately big O of 1 because k is approximately equal to 10, 12 max 20. The extra space complexity of Bloom filter is mu bit. It is calculated as minus n ln natural log epsilon divided by ln 2 whole square. So n is the total number of inputs and epsilon is the desired false positive probability. This is the comparison table between Merkle tree and Bloom filters. Building cost of Merkle tree is big O of n, where Bloom filter is big O of kl. Verification of a block in Merkle tree is big O log n, where Bloom filters takes big O k. Extra space in Merkle tree is big O n, in Bloom filter mu bits. The types of Merkle tree is deterministic and Bloom filter is approximation or probabilistic. We propose new variant of Merkle tree using hash and JOR operation, linked hash X for short, which is used to replace Merkle tree. Linked hash X maintain its root. Unlike Merkle tree, it doesn't maintain entire data structure. Linked hash X uses secure hash function like Merkle. So let HP, HB and HD be the previous hash value, the current hash value of particular block and desired hash value respectively. Then linked hash X can be defined as given in the equation 1. HD equal to HP XOR HB. So this is a elaboration of equation 1, and HR is the final hash value in the equation 2, and HR dash is the final hash value of equation 3. Linked hash X publishes two roots, H dash root and H root. H root is equal to H hash of H root HR, and H dash root equal to hash of H dash R. And this H R and H dash are kept private. This is the comparison cost between Merkle tree and linked hash X. Merkle tree building cost is big O of n, and linked hash X is big O of L. Verification of block is big O of log n in Merkle tree, where linked hash X doesn't support partial verification of a data block. Verification of all blocks in Merkle tree is big O of n log n, and linked hash X is big O of L. Extra space complexity of Merkle tree is big O of n, where linked hash X big O of 1. Solution is HEX-BLOOM. In the construction process, it requires to construct linked hash X as well as Bloom filter. All hash values are inserted into Bloom filter. Similarly, the construction of linked hash X requires big O of L cryptography hash function and big O of L JOR operation. Bloom filter requires big O of L insertion operation with big O of KL non-cryptography or non-secure hash function. Non-secure hash function is much faster than the secure hash function. Bloom filter and the root of linked hash X are maintained for future use or future data verification process. The verification process requires linked hash X root and Bloom filter, which are downloaded from the trusted node or server. The linked hash X root contains the JOR value of all the hash values and the hash value of the final result, that is H root and H dash root. The partial verification process requires Bloom filter because linked hash X doesn't support partial verification of a block's authenticity and integrity. A block is verified in Bloom filter for its authenticity after completely downloading the block. At the same time, the user needs to reconstruct the linked hash X root. Thus, Bloom filter gives approximate verification of a block's authenticity and integrity. Linked hash X is constructed by the user while downloading the data blocks. When all process completed, the constructed linked hash X root is compared with the downloaded linked hash X root. And this is the comparison between HEX-BLOOM and Merkle tree. Building cost of Merkle tree is big O of n. Our solution is HEX-BLOOM is big O of KL. Extra spaces of Merkle tree is big O of n, where HEX-BLOOM takes mu bits. Verification of a block is big O of log n. HEX-BLOOM is big O of k. And network access for a single occasion is big O of L, whereas HEX-BLOOM provides in big O of 1 solution. And types of Merkle tree is deterministic. Our solution is approximate or probabilistic and deterministic. In this paper, we unearthed the drawback of Merkle tree and propose a new model to solve the issues of Merkle tree called HEX-BLOOM. HEX-BLOOM is significantly faster than state-of-the-art Merkle tree. Moreover, it consumes less memory than the state-of-the-art Merkle tree. We have demonstrated that the Merkle tree creates unnecessary network traffic, which is addressed in our proposal. State-of-the-art Merkle tree requires network access to verify a block, and therefore it is time consuming and its performance depends on the network latency. On the contrary, HEX-BLOOM depends on the Bloom filter to verify each block's authenticity. Therefore, it doesn't require network access in verification process of each block. Overall, HEX-BLOOM filter outperforms the state-of-the-art Merkle tree in every aspect. These are reference